This is AP Chem 2025 free response question number 2. As always, no guarantees on the accuracy or point distributions, but I am going to give it my best shot. So question 2 is combustion analysis part 1. So combustion analysis, ascorbic acid is used to determine chemical composition. It says the products are 0.24 moles of CO2 and 2.883 grams of H2O. Calculate moles of H2O. Wow, that is a... and then figure out the empirical formula. So pretty straightforward. Part 1, empirical formula. You're just going to take... Let's see if I have it here. So part 1 is you just take the grams, convert the moles, molar mass. They don't give you the molar mass, so you have to calculate that, but that's probably a 0.16 moles. From there, you're going to get moles of H. To get the empirical formula, you have to take the 2-to-1 ratio for H to H2O to get 0.32 moles of H. Since they give you the moles of CO2, which gives you the moles of C, because 1 mole of C for every mole of CO2. That's 0.24 moles of C, which is also the moles of O, because they told you that's the same. So you get the empirical formula. So that's going to probably be, I don't know, a point there or so. And then you take all the things, divide by the smallest number, which is 0.24. So you get an empirical formula of C1, H1.3301, which we do not want non-whole numbers. But since this is a 0.333, we take that times 3. So the empirical formula should be C3H4O3. Okay. Part B. It acts as a weak acid. Here's the equation. You have the monoprotic weak acid, and it says the following titration curves with 10 milliliters of ascorbic acid titrated using 0.0550 molar NaOH, and then give you the titration curve. So first part. Well, I'm going to show you first part, molar concentration of ascorbic acid, and then find the pKa, and then what's the value of the ratio of the ascorbic acid, ascorbate ion to ascorbic acid. So this one, for the molar concentration, you need to know that at the equivalence point right here, 16 milliliters of NaOH is added. Okay, so you got to use the 16 milliliters here, multiply it by the 0.055 molar NaOH. That gives you 0.00088 moles of NaOH. Since it's monoprotic, the moles of base equal moles of acid. So you take your moles of acid, divide it by the volume of the acid, which is 10 milliliters. That's given up here. And that was 0.0880 molar ascorbic acid. For the pKa, you need the half equivalence point. So half of 16, this is equivalence point. Half of 16 is 8. Go right there. Take the pH of that. That's about 4 or 4.1. So I estimated that to be about 4.1 is the pKa. Last part, the ratio here, you need to use, easiest way is probably using the Henderson-Hasselbalch equation. So you take pH equals pKa plus log of ascorbic ion to ascorbic acid. So 4.1 is this, 4.7 is the pH. I'm going to subtract the 2, get them both on the same side. That's 0.6 equals log of the ion to the acid. To get from this to this, just the ratio, we want to take 10 to the 0.6, and so that ratio is 3.98. Okay, next part. Let's see. Dehydro. Let's see here. Dehydroascorbic acid can be produced. Okay, so you react this I3 ion. Runs through trials. Da, da, da. Okay, so we have kinetics, and it says determine. So the rate law, explain how the data supports the conclusion that the rate is first order with respect to HASC, and then calculate the value of the rate constant. Okay, so I'm going to do this down here. For the first part, we want something that is changing for HASC, but not changing for I3. So if you look at trials 1 and 3, the triiodide ion is not changing, but this is changing, so I can use this data. And if this is doubled, the rate also doubles. Okay, so looking at, so you gotta make sure you specify the rates, the rate trials 1 and 3 with I3 constant, and then the ascorbic acid doubling in concentration, the initial rate also doubles, supports for first order with respect to ascorbic acid. To get the rate constant, you just take a trial, plug it into here, and then you gotta make sure you get the right units. So I just took trial 1, I plugged in the numbers, okay, and then I multiplied that out, divided it by this side here to get K by itself. So I got K to be 0.000455. And then your units on that are going to be molarity to the -1, S to the -1. Because you have molarity here, but you have 2 molarities on this side. So if you divide by molarity squared, I didn't write that out. Here. Divide by molarity squared. Then you're going to cancel out one of them. That's going to be M to the -1. Okay, last one. Triiodide ion is significantly more soluble than elemental iodine. Identified an intermolecular force between I3 negative and water that's not present between I2 and water that could explain the difference in solubility. So I'm going to be very honest in saying that I'm a little confused by this question because I2 has only London forces available. There's no dipole. It's not polar. It does not have hydrogen bonding. This triiodide also has London forces. Probably some more London forces than this one does, but it is also non-polar. It has 5 electron domains in the middle. It's a linear molecule. There's no dipole in it, and so what I said was, I just said it's linear, it's non-polar, but maybe the Coulombic forces between the negative charge and the I3 and the water charge, the positive end of the H2O, that might cause more solubility, but I'm going to put a big question mark by this one. I do not know for sure about this question. I'm not entirely certain. So that's number 2. There you have it.